Good morning, good afternoon, and good evening. My name is Kurt Rashid Estes, and I am about to present to you the connection between digital twin and microstructural modeling of concrete hydration and durability. First, what is digital twin? I will explain to you digital twin, its history, its importance, and its connection to chemistry. We will answer the questions: what is a digital twin? Its origin story, why it matters now, and its connection to chemistry. First, let's define a digital twin. A digital twin is a virtual model of a real physical object, system, or process that updates continuously using real-time data. Think of digital twin as a clone of sorts. It is a clone that mimics your every movement as it updates. And using this clone, you can observe the data of your body, like heart pump and blood vessels and your lungs, how the digestive system works, and so on. It's not just a simulation, it's a living, evolving digital replica connected to the real world. Whenever the real object changes, temperature, pressure, chemical behavior, structure, digital twin updates immediately. Digital twin can be used for engines and factories, human organs and weather systems, and chemical reactions and entire cities. They combine sensor data and physics-based models, and also chemistry models, plus AI to predict behavior before it happens. I will I will give you a brief history of digital twins. In the 1960s, during NASA's pioneering mission, during moments of crisis, NASA engineers forged physical twin models of spacecraft, famously utilizing them to troubleshoot and rescue the Apollo 13 mission. This was the genesis of a revolutionary concept, which would turn out to be the digital twin. In 2002, the term digital twin is born, made by Dr. Michael Greaves, articulated the groundbreaking definition during his Product Lifecycle Management, or PLM, research, proposing a dynamic digital counterpart for every physical product, laying the intellectual cornerstone for the future. In the 2010s, the IoT and big data revolution. It is fueled by the explosion of affordable, powerful sensors and massive data analytics. Digital twins transform from theory to reality. Industries like aerospace, automotive, energy, and healthcare embrace their power for unprecedented real-time insights. Now, in the 2020s, its omnipresence. Now, for the 2020s, the digital twin is now omnipresent, meaning that it is everywhere. Digital twins have permeated nearly every facet of our world, extending their transformative influence from smart cities and power grids to integrate climate models, advanced medical imaging, and pioneering material science, becoming an indispensable tool for innovation. So why are digital twins important in the world of modern science? Well, it has predictive intelligence, which can forecast failures, chemical degradation, and biological responses before they can even occur. This enhances safety and understanding about the original product. It also has real-time monitoring, which has live sensor data to measure temperature, chemical concentrations, and pH accurately, which allows observation of processes at macro and micro scales. You can also do experimentations without the risk of danger. You can safely test dangerous reactions, stimulate drug responses, or predict environmental effects, which can save time and resources. Using digital twins, you can also improve design and innovation to digitally test thousands of variations, which can accelerate the discovery of new molecules, catalysts, and new materials. Using digital twins, it is sustainable and efficient. It can optimize industrial plants, energy systems, and manufacturing to reduce waste and operate cleaner. Now let's move on to how chemistry and digital twins are connected. Well, digital twins are connected to chemistry because it can be used in chemistry. For example, molecular and microstructural modeling. Chemistry is fundamental, dictating how materials behave at the atomic level. Digital twins leverage this by using sophisticated models to simulate these intricate interactions. For example, in molecular dynamics simulations track atomic and molecular movement over time based on classical mechanics. They predict macroscopic material properties from atomic structure and interactions, allowing observation of processes like phase transition and diffusion. Another example is quantum chemistry models, QCMs, such as density functional theory or DFT, delve into the electronic structure of atoms and molecules. By solving the Schrödinger equation, they predict chemical reactivity, bonding, and energy levels, providing deep understanding of molecular interactions. Lastly, last but not least, microstructure simulations. These models bridge atomic level interactions and macroscopic material behavior. They simulate the arrangement and the evolution of grains, defects, and phases within materials, which can significantly influence the bulk properties like strength and thermal conductivity. This deep chemical insight is crucial for designing and optimizing these following inventions, like stronger materials, which can enhance mechanical properties by simulating atomic arrangements and defects for novel alloys and composites. Advanced batteries, which can optimize electrode materials and electrolytes to improve ion transport, energy density, and charging capabilities. Next is the novel polymers or pharmaceuticals, which can accelerate discovery by virtually screening molecular structures for desired properties like drug efficacy or polymer elasticity. Lastly, next are novel polymers and pharmaceuticals. Digital twins can accelerate discovery by virtually screening molecular structures for desired properties like drug efficacy or polymer elasticity. Last is the corrosion prevention systems. This can simulate electrochemical reactions to develop resistant coatings and corrosion inhibiting alloys, extending the equipment's lifetime. Now, let's tackle how digital twins and thermodynamics are related to each other. Digital twins extensively rely on the principles of thermodynamics to simulate and predict behavior in various chemical and physical processes, ensuring an accurate digital representation of the real world's assets' energy dynamics. The key thermodynamic principles in digital twins are heat transfer. Digital twins can model how energy moves through conduction, convection, and radiation to predict thermal profiles, which can optimize cooling and prevent overheating. Another principle is entropy and enthalpy. Digital twins can predict the spontaneity and energy changes of reaction and processes. Enthalpy quantifies heat absorbed or released, and entropy measures disorder, together determining spontaneity via Gibbs free energy. Another principle are the phase changes. Digital twins can simulate the transitions between solid, liquid, and gas states, predicting when a substance will change phase and the energy required. Lastly, but not least, are the equilibrium states, which can determine stable conditions in complex systems by predicting the final stable state, including chemical and phase equilibrium. These thermodynamic models for optimizing and ensuring the safe and efficient operation of a wide array of industrial assets like chemical reactors, power plants, and materials that are exposed to extreme heat. Next, I will tackle how electrochemistry and digital twins are related to each other. Electrochemistry, the study of electricity and chemical reactions, is crucial for modern technologies. Digital twins accurately simulate these interactions, predicting performance and optimizing parameters for enhanced efficiency, safety, and longevity in real-world assets. The key electrochemical principles modeled by digital twins are ionic transport. Digital twins model the movement of charged particles or ions in electrolytes, impacting the conductivity and reaction rates. Another principle is the electron flow. These trap electron movement through circuits and electrode materials, critical for current and reaction kinetics. Last but not the least are the processes. Digital twins can predict oxidation reduction reactions or electron transfers, which is fundamental to electrochemical energy conversion. By accurately modeling these principles, digital twins enable advanced development and optimization across without applications of batteries. By accurately modeling these principles, digital twins enable advanced development and optimization across various applications. These applications can include batteries and fuel cells. Digital twins can simulate charge and discharge. It can also show energy density and degradation to enhance performance and lifespan. Another one of these applications are corrosion prevention, which can predict material degradation under environmental conditions to design effective protective strategies. Another example are advanced sensors. Digital twins can improve accuracy, sensitivity, and responsiveness by modeling electrode to analyte interactions. Last but not least are biomedical devices. Digital twins can optimize biocompatibility, signal transduction, and stability for reliable diagnostics and therapies. Last but not the least of how digital twins are connected to chemistry, we will tackle how environmental chemistry and digital twins are related. The key environmental processes that are modeled by digital twins are soil chemistry, which digital twins can model the movement and transformation of nutrients and pollutants. These can include nutrient cycling, contaminant degradation, and heavy metal absorption. Another process that are modeled by digital twins are atmospheric dynamics. Digital twins can simulate dispersion of airborne chemicals, can track greenhouse gas concentrations, and predict atmospheric reactions to forecast air quality. Last but not least are hydrology and water quality. Digital twins can model chemical transport in aquatic systems, which can include pollutant spread, sediment transport, and impacts on aquatic ecosystem health. The advanced applications that are enabled by digital twins are how digital twins can predict pollution spread. It can forecast movement and impact of contaminants for rapid response and targeted cleanup. Digital twins can also forecast rainfall chemistry. It can predict chemical compositions of precipitation, for example, acid rain or nutrient deposition, to assess ecosystem impacts. Last but not the least, it can also simulate climate behavior. Digital twins provide high resolution simulations of regional climate behavior used in modeling complex feedback loops and supporting adaptation strategies. To sum it all up, digital twins are more than digital models. They are scientific tools that blend engineering, chemistry, physics, data, and AI to a single powerful system. From their origins in NASA missions to their critical role in modern industries, digital twins have transformed how we understand and manage the world. By integrating advanced chemistry from reaction kinetics to thermodynamics and material science, digital twins empower us to predict, monitor, and improve everything from microscopic molecules to massive infrastructures. This holistic approach drives innovation, enhances efficiency, and fosters sustainability across diverse fields. That's it for digital twin. Now let's move on to microstructural modeling. Now we will move on to the microstructural modeling of concrete, hydration, and durability. Concrete has a complex nature. Even though it is the most widely used construction material globally, which forms the backbone of our infrastructure, it is far from being simple, uniform substance, since it is a complex composite engineered from cement, water, aggregates like sand and gravel, and various chemical admixtures. It says here that microstructure determines performance. Its performance, longevity, and resistance to environmental stressors are intrinsically linked to its microstructure, which encompasses the intricate arrangement of hydration products, the size distribution on and connectivity of pores, the mechanisms of microcrack formations and propagation, and the pathways for transport of water, ions, and gases. A deep understanding of these microscopic features is crucial for material scientists and civil engineers. It allows them to develop strategies to. So, what is microstructural modeling? Microstructural modeling employs advanced computer simulations to accurately replicate the intricate chemical and physical processes that occur within concrete at a microscopic level. These sophisticated models are capable of simulating a wide array of phenomena, providing a virtual window into concrete's behavior. The features of microstructural modeling are, but not limited to, simulating hydration reactions, the formation of products, the observation of pore structure evolution, the mechanics of cracks, and substance inverse. Essentially, Microstructural modeling constructs a highly detailed microscopic digital twin of concrete, enabling virtual experimentation and analysis without the need for physical prototypes. Now, let us move on to the chemistry behind concrete hydration. Hydration is the fundamental chemical reaction between cement minerals and water that transforms a plastic paste into a hardened, durable material. This exothermic process is responsible for concrete setting and hardening. The main cement compounds that are involved in the hydration process are tricalcium silicate, dicalcium silicate, tricalcium aluminate, and tetracalcium aluminiferrite, which has their own purposes in the hydration process. Now, let us look at the primary hydration products. These are calcium silicate hydrate, which is an amorphous gel, which is the main binding agent between the cement and the water, which acts like a glue that provides concrete with its mechanical strength and cohesive properties. Next is one of the most important parts of concrete, which is the calcium hydroxide. It is a crystalline product that contributes to pH buffering but can also be a site for chemical attack. Last but not the least is ettringite and monosulfate phases. It is formed from the reaction of C3A. These phases play roles in early strength and can be involved in sulfate attack if conditions are unfavorable. These complex reactions collectively generate significant heat, which leads to the formation of a dense, solid gel structure and progressively reduced porosity within the cement base. All these phenomena are interdependent and crucial for the development of concrete's ultimate strength and long-term durability. Now, let us go over the various types of microstructural models in the world. Various modeling approaches are employed to capture the diverse aspects of concrete microstructure and behavior. Each type offers unique advantages for specific investigations. First of the examples of microstructural models are lattice models. These models represent concrete as a discrete network of interconnected elements. They are particularly effective for studying fracture mechanics, crack growth, and damage evolution under stress, providing insights into the material's failure behavior. Next are particle-based models. These focus on individual cement grains and simulate their dissolution and the subsequent growth of hydration products over time. They are excellent for visualizing the evolving microstructure and porosity from initial mixing to full hydration. Next are finite element models, or FEM, widely used for detailed analysis of stress or strain distribution, thermal behavior, and durability-related transport phenomena within the complex concrete matrix. Next are thermodynamic models. These models predict the stable chemical phase assemblages that form within concrete under varying environmental conditions, such as temperature, humidity, and exposure to aggressive chemicals. Last but not the least are integrated models. Advanced models like CAM Hyde 3D, Hymastruck, and Micro IC combine multiple approaches to simulate the interplay between hydration kinetics, microstructure development, and the resulting durability parameters, offering a holistic view. Now let us move on to how concrete is modeled for durability. Durability modeling is crucial for predicting how concrete structures will perform and deteriorate over their design service life, often spanning many decades. These models simulate various degradation mechanisms. The types of models that are used in modeling durability are, but not limited to, chloride ingress modeling, carbonation modeling, sulfate attack modeling, freeze-thaw modeling, and alkali silica modeling. First, chloride ingress modeling. Chlorides from sources like seawater or de-icing salt penetrates the concrete pores network, depassivating the steel reinforcement and initiating corrosion, which can lead to cracking and spalling. Next is the carbonation modeling. Atmospheric carbon dioxide reacts with calcium hydroxide in the concrete, reducing its alkalinity. This loss of pH weakens the passive protective layer on steel reinforcement, making it susceptible to corrosion. Next is the sulfate attack modeling. Sulfate ions from groundwater or industrial waste react with cement hydration products, leading to deformation of expensive minerals like ettringite and gypsum, which cause internal stresses, cracking, and ultimately material disintegration. Next are freeze-thaw modeling. In cold climates, water absorbs into concrete pores, freezes, and expands, generating internal pressures. Repeated cycles of freezing and thawing cause microcracking, leading to the surface scaling and structural damage. Last but not the least are alkali silica reactions, or ASR. Alkaline pore solutions react with certain reactive silicate bases in aggregates, forming an expansive gel. This gel absorbs water, swells, and induces internal stresses, leading to a map cracking and structural distress. Microstructural models are indispensable for predicting the rate and severity of these degradation processes by simulating complex phenomena such as ion diffusion, crack growth kinetics, and detailed chemical reaction pathways. Now, let us discuss how important microstructural modeling has been for civil engineers and chemists alike. Microstructural modeling is not merely an academic exercise. It provides critical benefits that are transforming the field of civil engineering and materials science. These importances are enhanced prediction of performance because it significantly improves the prediction of concrete's long-term behavior and performance under various environmental and loading conditions, extending its service life. Another one is that microstructural modeling can optimize concrete design. Models facilitate the design of more durable concrete mixes specifically tailored for diverse applications, from high-rise buildings to critical infrastructures like bridges and dams. Microstructure modeling also offers cost reduction by enabling better material design and performance prediction. It helps in reducing substantial maintenance and repair costs over the lifespan of structures. It can also offer sustainable material development. The methodology supports the development and optimization of low-carbon cement and concrete alternatives, addressing pressing environmental concerns. Last but not the least of these importances are resource efficiency. By optimizing material composition and performance, it enhances sustainability through more efficient resource utilization and reduced waste. Much like digital twins are revolutionizing complex engineering systems, microstructural modeling provides a powerful virtual laboratory for concrete. This allows researchers and engineers to conduct extensive testing and scenario analysis without the time and expense of constructing numerous physical samples, accelerating innovation and understanding. Now that we have gone over the importance of microstructural engineering, let's move on to the challenges in using or making microstructural modeling. Despite its immense potential, microstructural modeling of concrete presents several inherent challenges that researchers are actively working to overcome. One of these challenges are high computational cost. Simulating complex chemical and physical processes at a microscopic scale requires significant computational power and time, especially for large volumes or long durations. Microstructural modeling also finds it hard to capture real world complexity, translating the heterogeneous and dynamic nature of real concrete with all its inherent variabilities into accurate and predictive models remains a complex task. Another one of these challenges are precise material characterization. The accuracy of models relies heavily on precise input data regarding material properties and reaction kinetics, which can be challenging to obtain experimentally. Last but not the least of these challenges are multi-scale modeling needs. Making reliable and long-term predictions. Last but not the least of these challenges of microstructural modeling are multi-scale modeling needs. Making reliable long-term predictions necessitates integrating models across multiple scales, from atomic to macroscopic, a significant research frontier. Nevertheless, continuous and rapid advancement in computing hardware, sophisticated numerical algorithms, and a deeper understanding of material science are steadily improving the accuracy, efficiency, and predictive capabilities of these models, pushing the boundaries of what is possible. In conclusion to all of this, microstructural modeling stands as an incredibly powerful and versatile tool, offering profound insights into how concrete hardens, gains strength, and ultimately deteriorates. By seamlessly integrating principles from chemistry, physics, and advanced computer science, this field empowers engineers to design concrete structures that are not just functional, but demonstrably safe, stronger, and longer lasting. This innovative approach is not just an enhancement, it is essential for the development of modern, resilient infrastructure, driving sustainability initiatives, and shaping the very future of construction material science. It allows us to move beyond empirical design to a scientifically grounded, predictive understanding of concrete's performance. Now, finally, I will explain to you the chemistry behind digital twins and microstructural modeling of concrete hydration and durability and how they are related to each other. Concrete's behavior begins with integrated chemistry of cement hydration, a process meticulously analyzed by microstructural models. When cement comes into contact with water, its major compounds, tricalcium silicate, dicalcium silicate, tricalcium aluminate, and tetracalcium aluminum ferrite initiate exothermic reactions. These reactions are critical for the formation of dehydration products, notably calcium silicate hydrate, which is the primary contributor to concrete's mechanical strength and stiffness, and also calcium hydroxide, which plays a significant role in governing pH levels within the concrete matrix and influencing its susceptibility to carbonation. As hydration progresses, these uniform products gradually fill the microscopic spaces between the organocement grains, leading to a progressive reduction in porosity. This dynamic evolution of the microstructure directly influences the development of brace for moisture movement, and ultimately, the overall durability of the concrete. Microstructural modeling provides a sophisticated computational framework to simulate this entire chemical process. It accurately predicts crucial parameters such as heat release kinetics, the degree of hydration over time, the refinement of the pore structure, and the early age development of the internal structural network of the concrete, offering a comprehensive understanding from initiation to maturation. Digital twins leverage these detailed chemical predictions as the foundational layer for their virtual behavior models. By continuously comparing real-time sensor data encompassing parameters such as internal temperature, relative humidity, internal moisture content, and exothermic heat generation to the expected chemical reaction rates derived from the microstructural models, the digital twin dynamically updates its understanding of the actual hydration progress. This continuous feedback loop allows the digital twin to learn and adapt to the true chemical evolution occurring within the concrete structure, leading to increasingly realistic, precise, and accurate predictions of material properties and performance over its service life. For concrete durability is fundamentally governed by a suite of long-term chemical processes. Microstructural models are designed to simulate these complex interactions, while digital twins provide real-time tracking and predictive capabilities. One of the most significant processes is chloride ion transport, where aggressive chloride ions, typically originating from marine environments or de-icing salts, ingress and diffuse through the intricate pore network of the concrete. This diffusion rate is intricately controlled by critical factors such as the pore size and distribution, the prevailing moisture content in the concrete, and the chemical binding capacity of the various hydration products. Microstructural modeling precisely calculates how the pore structure changes over time, how chloride ions interact chemically with the different cementitious spaces, and critically, predicts the time frame when these corrosive ions will reach the surface of the reinforcing steel. Digital twins significantly enhance these predictions by integrating real-time chloride sensor data, allowing for a highly accurate dynamic forecast of corrosion initiation, which is pivotal for proactive maintenance. For carbonation effects, carbonation is another crucial chemical degradation process where atmospheric carbon dioxide reacts with calcium hydroxide in a concrete to form calcium carbonate. This reaction leads to a significant reduction in the concrete's pH, which subsequently destroys the protective passive film that naturally forms on the steel reinforcement, thereby enabling corrosion. For modeling and monitoring these models, microstructural models are employed to estimate the depth of carbonation based on the concrete's chemical composition and evolving porosity. Digital twins further refine these estimations by continuously collecting and incorporating real-world data on environmental humidity, the actual exposure of levels of CO2, and ambient temperature fluctuations. In conclusion, corrosion itself is an electrochemical process involving the oxidation of iron. Digital twins are uniquely equipped to detect the onset and progression of these processes through the integration of embedded corrosion sensors, which provide invaluable real-time feedback. By synergistically combining sophisticated chemistry-based models with continuous real-time monitoring, engineers gain an unparalleled ability to predict concrete deterioration with far greater accuracy and lead time than either method that could achieve independently, enabling more effective structural management and extending service life. In conclusion to everything that I have just said from start to finish, creation of digital twins and microstructural modeling represents a major advancement in understanding and predicting the performance of concrete structures. Microstructural modeling reveals the fundamental chemistry of hydration, pore development, and deterioration, providing a scientific explanation for how concrete evolves over time. Digital twins build on this foundation by incorporating real-time data sensors, bridging the gap between theoretical predictions and actual field behavior. Together, they create a dynamic, continuously updated system capable of forecasting durability, identifying early signs of deterioration, and supporting more effective maintenance and design decisions. This combined use of chemistry, modeling, and digital technology not only enhances structural reliability but also sets the stage for more resilient, sustainable, and long-lasting infrastructure. That's all for this video. Thank you.